To make sure you're properly preparing for your first exam with the material we covered in Chapter 2, I put together a few practice questions for us to discuss. So looking at this first question, it's true or false. In liquid water, the average water molecule forms hydrogen bonds with 3 to 4 other water molecules. Every single water molecule has the ability, theoretically, to create 4 hydrogen bonds, so one water molecule can theoretically bind to 4 other water molecules. In reality, because the bonds are constantly being made and broken, we actually see that on average, one water molecule can bind to 3.4 water molecules. So that makes this a true statement. Make sure for your first exam that you can draw one water molecule properly hydrogen bonded to the theoretically possible 4 other water molecules. Next question, true or false? Individual hydrogen bonds are much weaker than covalent bonds. The key word here is individual. This is a true statement. A single hydrogen bond is much weaker than a single covalent bond. Where this becomes tricky is when we start to consider things like the tertiary structure of a protein, and we see hundreds of hydrogen bonds helping to hold this overall structure in combination with other types of interactions such as hydrophobic interactions. And so then we start thinking about hydrogen bonds actually being quite strong, but an individual hydrogen bond is weaker than a covalent bond. Next question. Individual hydrogen bonds in liquid water exist for many seconds and sometimes for minutes. This is completely false. Hydrogen bonds are very short-lived. That is one of their advantages. Because they are a weaker bond, they can be made and broken. What is a hydronium ion? There's many ways to answer this question. If we're thinking about ionization of water, then the hydronium ion is going to be the predominant state in which we see the proton. So we can answer this question with a few answers. We can give the chemical structure of a hydronium ion, which is water plus a proton. We can simply define a hydronium ion as a hydrated hydrogen ion or a hydrated proton. Any of those would be acceptable answers. What is the pH of a solution of 0.1 molar sodium hydroxide? Given in this problem, we have the hydroxide concentration, not the proton concentration. So we can't use straight away the generic pH is equal to the negative log of the proton concentration equation. We will calculate the pOH from the negative log of the hydroxide ion concentration, and then use the knowledge that the pH is going to be equal to 14 minus the pOH. To solve the problem, we'll say the pOH is equal to the negative log of 0.1, given here as the hydroxide ion concentration. This tells us the pOH is 1. If the pOH is 1, then the pH will be 14 minus 1, or 13. The answer to the problem is 13. What is the predominant ionic form of phosphoric acid at pH 3.2? Phosphoric acid is a triprotic acid, meaning it has 3 ionizable protons. Given in the problem are the 3 pKa's for those 3 protons that are capable of leaving the phosphoric acid based on the pH. So as we go to a pH of 3.2, we are above this first pKa of 2.14, so we are going to lose all of those first protons. At pH 3.2, we have not gotten to the second pKa, so the predominant form we see would be the phosphoric acid with 1 proton gone, shown here, H2PO4. True or false? When pH equals pKa, the weak acid and conjugate base concentration in a buffer are equal. This is a true statement, as this is the basic definition of a good buffer. This should really trigger to you that it's important for you to understand how to read a titration curve In the past, on a first exam, I have asked students to draw a titration curve, labeling the axes, identifying the best buffering range, which is +1 and plus minus the pKa, +1 and -1 the pKa. So it's really important to be comfortable with those titration curves. And then the last practice problem that I have in our little review is a buffer problem using the Henderson-Hasselbalch equation. So we have a weak acid with a pKa of 5.0. If 1 mole of the acid and 0.1 moles of sodium hydroxide were dissolved in 1 liter of water, what would the final pH be? So the good thing about this problem is you end with this final volume of 1 liter, so you can ignore the volume and work with your moles. What you have to do is identify what is my HA and what is my A minus. My A minus in this problem is going to come from the amount of sodium hydroxide that I've added. The sodium hydroxide that I've added is going to pull and steal away from my HA. My HA is 1 mole. So when I set this up, I'm going to have 0.1 mole of A minus and 1.0 minus 0.1 moles of HA. So what this is going to look like in the Henderson-Hasselbalch equation is the pKa plugged into the formula 5.0 plus the log of A minus, so 0.1, divided by HA, 0.9, giving me a final pH of 4.05. Now, the only thing I did not put any practice problems in that are really important for you to study would be things like the blood buffering system and acidosis that we looked at. It is important to know the reaction that occurs when carbonic acid ionizes into a hydrogen ion and bicarbonate. And then it's also important to make sure you understand the hydrophobic effect